In this mini lecture, I'm going to talk about indefinite integrals and then something called the net change theorem, which is just a slightly different way of reimagining the fundamental theorem of calculus. So to start with that, the fundamental theorem of calculus, we've looked at that here before with definite integrals, and that really provides a strong connection between the idea of an antiderivative and then this idea of the definite integral. And the definite integral we developed to find the area under a curve, and you wouldn't think that would have anything to do with derivatives, but it turns out that it does. So this antiderivative is an important mathematical concept, so it would be nice to have a better notation to represent it. And what's been developed is this thing that we call the indefinite integral. So if we have a function capital F prime of x that's equal to f of x, so that means the derivative of capital F is little f. Well, that means then to go from little f to capital F, I'm doing an antiderivative. So we say capital F of x is an antiderivative of little f of x. But then we write this: the integral of f of x dx is equal to capital F of x. So when I take this integral of my little f, I get the antiderivative. Now this is the same notation, of course, we used for a definite integral, but we don't have limits of integration, right? We're not saying the integral from a to b, we're just saying the integral. And that's where it changes from definite is over a particular interval, to indefinite, which is not evaluated for a particular interval. So I've discussed that a little here, and what that means then, when I take a definite integral, I get a numerical value. The definite integral is a number. An indefinite integral is a function, and actually it's a family of functions, which we'll look at a little bit here. So in these examples, I picked these to be a little bit easy. Integral from 1 to 3 of 2x dx. Now this is a definite integral, it has limits of integration. So to do that I need an antiderivative of 2x. Well, to do an antiderivative of 2x, when I take the derivative, the exponent goes down 1. So to take an antiderivative, it goes up 1. So that's going to be x squared. And then I have to divide by the new exponent 2. And here that's going to be evaluated then between 1 and 3. Oh, I left off my 2. So 2x squared over 2, right? So I had my 2x here. So that 2 becomes this 2. The x becomes x squared, and then I have to divide by the new exponent. So that just gives me x squared then evaluated between 1 and 3. So that's just 3 squared minus 1 squared. That's just 9 minus 1, which is 8. So a definite integral is just equal to a number. This indefinite integral, I take the antiderivative the same way, and we get x squared. But we have this idea we talked about before. When a function doesn't have a unique antiderivative, yes, the derivative of x squared is equal to 2x. But if I had x squared plus 1, its derivative is also 2x. Or if I had x squared plus 7, its derivative is 2x. Or if I have x squared minus 3, its derivative is 2x. And so I get all these antiderivatives. Essentially what I have to do here is say then my antiderivative is x squared plus c. So the definite integral has an answer of 8. The indefinite integral has an answer of x squared plus c. That c is called the constant of integration, and it's an essential part of the indefinite integral. You need to include plus c at the end all the time when you take an indefinite integral. What that's showing then, my antiderivative is the function x squared, and of course we know the graph of x squared, that would be this blue graph here, my normal parabola x squared. But I could take different values of c. My value here of x squared, the blue graph, has a y-intercept of 0, and that would correspond to c equals 0. But if I had x squared plus 3, that would move up 3 units. X squared plus 6 would move up 6 units. X squared minus 4 would move down 4 units. All of these parabolas, all 4 of them that I have graphed here, are all part of this solution to this indefinite integral. And of course, these are only 4 specific examples. There are actually infinitely many graphs that would be solutions for this indefinite integral. And so that's what I mean by saying we have a family of functions that's the solution to this indefinite integral. So, to evaluate both definite and indefinite integrals, then, it's important to find antiderivatives. Now, in the last mini lecture, I talked about these same formulas. This is just a little bit better notation here for finding them. Remember, this integral symbol just means the antiderivative. So the antiderivative of a constant times a function is just the constant times the antiderivative of the function. The antiderivative of the sum of 2 functions is just the sum of the 2 antiderivatives. And what we could add on here, we could throw in a minus as well, right? If we subtract functions, it works the same way. The integral of a constant is just the constant times x. And again, plus c, though, what we would have here. The integral of something to a power, we increase the power plus 1, and we divide by the new power, and then we have to have plus c. Notice this doesn't work if n is negative 1. If I have x to the negative 1, which just would be 1 over x, right? So x to the negative 1 dx, which is the integral of 1 over x dx. For now, we don't know what that is, okay? This formula only works if n is not equal to negative 1. If I have negative 1 in my exponent, that's the integral of 1 over x. This rule doesn't work, and I don't know what that antiderivative is. At MSJC, at least, we talk about what this antiderivative is in Calc 2. It actually involves, it becomes the natural log. That's where we get logarithms involved, is with this kind of integral. And then these are just the trigonometric sort of reversals of the differentiation rules. We knew the derivative of sine was cosine, so the antiderivative of cosine is just sine. The derivative of cosine was negative sine. So if I take the antiderivative of sine, I get negative cosine. The rules, are reversed here. So again, the derivative of tangent was secant squared, so the antiderivative of secant squared is just tangent. The derivative of cotangent was negative cosecant squared, so if I take the antiderivative of cosecant squared, it's negative cotangent, right? Those signs have to be reversed. And then the same thing here. The derivative of secant is secant tangent. The derivative of cosecant would be negative cosecant cotangent. So I've got these anti-differentiation rules, these antiderivatives here. Just as a note, an elementary function is a function of a single variable composed of particular simple functions. So we put these simple functions together in different ways. So typically we define that then as a sum or a product and or a composition of finitely many polynomials, rational functions, that's where my variables in the top and the bottom, trigonometric functions, exponential functions, that would be 2 to the x, 4 to the x, stuff like that, and their inverse functions, so inverse trigonometric functions and logarithmic functions and all of that. Now, we haven't talked about all of these kinds of functions in calculus yet. We've talked about trigonometric functions. We haven't done exponential functions yet. We haven't done inverses yet. But if we had, it's relatively easy to develop differentiation rules that would allow me to evaluate the derivative of every elementary function. By the end of Calc 2, any basic function that any mathematician could write down for you, you would know the rules to take the derivative. However, the problem of finding the antiderivative is much more complicated. In fact, there are relatively simple elementary functions that have no nice antiderivative. One of these is sine of x squared. It's really easy to take the derivative of sine of x squared. It's just a chain rule problem, right? The derivative of sine of x squared, well, the derivative of sine is cosine, but then I'd have to take the derivative of the inside. Not that. Cosine of x squared. So that would be the answer for the derivative. But there's no antiderivative. You can never take the antiderivative of this function and have it expressed in what's called closed form. Now, you can find a function that's the antiderivative, but you need to represent it as an infinite polynomial. That's something you'll look at in Calc 2. Now, all of this is just a long way of saying that taking antiderivatives, evaluating these integrals, is much more complicated than just taking derivatives. Antiderivatives are more complicated. That's why in Calc 2, one of the big topics we talk about are techniques of integration, or techniques of taking antiderivatives. And it's much more complicated than taking derivatives themselves. Now, we've got this thing then called the net change theorem. This is just a rewriting of the fundamental theorem of calculus that makes certain applications, especially that might come from science or engineering, or physics, easier to sort of represent. So, the fundamental theorem of calculus says that if capital F is an antiderivative of little f, then when I take the integral from a to b of little f, I just take the antiderivative, I evaluate it at the top and the bottom, and I subtract. And that's what that's saying right there. But if capital F is an antiderivative of little f, if it's an antiderivative, that means that if I take the derivative, I get back to little f. So capital F prime of x is little f. So instead of the integral of little f, I could have the integral of capital F prime of x, right? Those are the same thing. So that would be capital F of b minus capital F of a. So if I take the definite integral of the derivative of a function, I get back to the original function evaluated just at these endpoints and subtracted. Well, when I subtract function values, I'm finding the net change in the value of the function. So if I take the integral of the derivative of a function, I get the net change in the value of the function. So if we integrate the rate of change of a function, we can calculate the actual change in the value of the function. Now, this is a net change, and I'll talk about this in example 2 down here. But part 1, let's say capital V of t, although it applies to 1 too, so I'll talk about it here. Let capital V of t represent the volume of water in a reservoir. So we have this reservoir, dammed up river, and the volume is changing over time. Of course, at certain times of the year, that change would be positive. Snow melt would be coming in maybe from the Sierras, and the reservoir would be filling up with water, and then V prime of t would represent the rate at which the volume of water in the reservoir is changing over time. So again, in the spring, V prime of t would probably be a positive number. So then if I integrate V prime of t, well, in taking the integral of the derivative gets me back to the original function, but I have to evaluate it at these endpoints. So capital V of b minus capital V of a. So it represents the difference in the volume of water in the reservoir between time A and time B. Right? We take the volume that's there at time B, we subtract the volume at time A. Now, that doesn't necessarily represent the total amount of change of water in the volume. The water level could have gone up and then down and then up. And so if this is A and this is B, then when I do the integral, it just represents that net change, right? It doesn't take into account that the volume went up and down and then up again, all right? It doesn't take into account the total amount of water that's entered the reservoir. It just represents the change between time A and time B. Number 2, so if S of t represents the position function of an object moving in a straight line, and we've talked about that kind of thing, then if I take the derivative of the position function, S prime of t, we call that the velocity function of the object, and we represent that with V of t. So if I take the integral from a to b of S prime of t, and that's really the integral from a to b of V of t, right? If I integrate the velocity function, that gives me then S of b minus S of a, the position at times b minus the position at time a. That represents then the net displacement of the object between time a and time b. Now, this is not necessarily the total distance that the object has traveled between those two times. It represents the change in position of the object. My object may have traveled backwards. So I'm here at time a. Maybe the object travels forward for a while, then backward for a while, and then forward again, and that's time b. Now, time b. I want to label that. Okay, so it's moved from this position at time A to the position at time B. And so I've changed position going between those two. This integral does not capture the total distance that this object has moved, though, because it moved positive for a while, and then negative, and then positive for a while. So this integral only captures this distance between A and B, not the distance that this object has traveled. This setup can be very helpful for particular applied problems in science or engineering.